am Algene Grace A. Badajos, and today I will discuss about the significant figures. Now, in a measurement, the number of digits that represent a reasonable reliable information is called significant figures. It is only the last digit that is estimated figure. Significant figures are important in experimental measurement and calculation. The number one example is all non-zero digits are significant. So, 565 centimeter. 565 centimeter has three significant figures. Other example, 3,164 centimeter. 3,164 centimeter has four significant figures. Number 2. Zeros between non-zero digits are significant. So, 603 centimeter. 603 centimeter has three significant figures. 30,513 meter. 30,513 meter has five significant figures. Number 3. Zeros to the left of the first non-zero digit are not significant. For example, 0.006 kilograms. 0.006 kilogram has only one significant figure. Why? Because these zeros give only the position of a decimal point. Number 4. All zeros written to the right of a decimal point of a number greater than 1 are significant. For example, 5.0 meter. So, 5.0 meter has two significant figures. Number 5. If a number is less than 1, zeros at the end of a non-zero digit and the zeros between non-zero digits are significant. For example, 0.40 degrees Celsius. So, 0.40 degrees Celsius has two significant figures. Number 6. For numbers that do not contain decimal point, zeros to the right may or may not be significant. This can be expressed in scientific notation to really the numbers of significant figures. For example, 6 times 10 to the power of 3. So it has one significant figures or 6.0 times 10 to the power of 3. So it has two significant figures, or either we could write as 6.00 times 10 to the power of 3. So, it has three significant figures, or we could also add 0 and so on.
Looking at the numbers, which ones will you write? There are so many zeros coming at you from all sides. Zeros at the beginning are never civics. Captive zeros are always significant. Beginning is never, the middle is always the end. Yes, dot, no dot, no. Beginning is never, the middle is always the end. Yes, dot, no. Then it comes down to the zeros at the end. You gotta look to the decimal, my friend. If there's a dot there, the zero at the end has significance. If there's no decimal, it's time to say good riddance. Beginning is never, the middle is always the end. Yes, dot, no. Beginning is never, the middle is always the end. Yes, dot, no. Now it's time to do the math. When you multiply, look for the weakest link. Then when you add or subtract, look at the DAD. Just think, beginning is never, the middle is always the end. Yes, dot, no. Beginning is never, the middle is always the end. Yes, dot, no. Beginning is never, the middle is always the end. That's it, fix my
Some numbers are really big, some numbers are really small. I wish there was a way to easily express them all. Hey, I found there's an easy way to show extreme scientifically. Scientific notation does it easily. And now I love science more than I ever did before, can't you see? Express your number so that it's more than 1, but less than 10. Take that number and multiply it by 10 to the proper exponent. 300 in scientific notation is 3 times 10 to the power of 2. 10 to the power of 2 is 100 times 3, that's 300, so there's your proof. Scientific notation uses exponents with the base of 10, so you don't have to write out so many zeros again and again and again. Take a number like 0.0023, plug it into a times 10 raised to the power of b, where a equals 2.3 and b is -3. You get 2.3 times 10 raised to the power of -3. Express your number so that it's more than 1, but less than 10. Take that number and multiply it by 10 to the proper exponent. 0.03 in scientific notation is 3 times 10 to the -2. 10 to the -2 is 0.01 times 3, that's 0.03, so yeah, there's your proof.